So, welcome to Pattern Analysis. We have our first actual meeting today to talk a bit about content. Most of the material is kind of a repetition, but I somehow wanted to pick you up from somewhere and then start from some joint position together then into the new material. Yeah? We can talk about this in a minute. I tell you in advance, we will have to finish this meeting today 10 minutes past 5. It's like a special arrangement today. I'm sorry for the rush. In the future, we will go the whole distance, of course. Before we start in this content, let me bring something to your attention. And this is the so-called Ferienakademie. If you are already for a while at FAU, you are probably aware of it. It's a summer school, even though it's like fall almost. And it's in northern Italy. It's very selective. There are different courses offered. You can apply for these courses, and the reason why I'm mentioning this is the courses are always between someone from FAU and someone from TU Munich or FAU in Stuttgart or TU Munich in Stuttgart. So the reason why I'm mentioning this is because I'm also offering a class here on secure and explainable machine learning. Explainable is, let's say, the explainable in a physical or differential equation type of sense. The security part is, let's say, my part here. It's a very nice summer school. I'll also send an email around. You can have a look at the website www.ferienakademie.de if you're interested. It's very selective. You need to have good grades in order to get in. But still, I want to encourage you to take this into consideration because it is a very nice opportunity, and it's kind of special for these three universities, FAU, TU Munich, and Stuttgart. The deadline will be in early May, so there are still, let's say, almost 2 weeks to think about this, but then applications have to be there. Okay. About pattern analysis. We had a couple of slides and an associated video on some foundations here. What are data? What are distributions? What is their connection, in particular with these generative models? Some other basic concepts, essentially repetitions. What are parameters, hyperparameters? And then 2 or 3 methods, actual methods. Yeah? One method is this inversion sampling. The other one are the Parsons window estimator. So essentially non-parametric density estimation, but in particular the Parsons window estimator and the k-nearest neighbor density estimator. The rest should be known in one way or another. There's a bit of a comment on bias and variance. But of course, the reason why we are meeting here is to have a conversation about these things, to use this opportunity to catch up on something that might not be clear or that you want to emphasize a bit more. And I also brought, let's say, 3 questions that I think are worth emphasizing because I think these are important points that should be understood. And they will not take us an eternity to answer. So if we think about time limits or anything, we can do this very quickly. So there's enough space for things that you also want to discuss But in any case, we can also have a look at these 3 questions then very soon, if you like. But before we do that, I wanted to check with you whether there are particular topics that you would like me to address or that you want me to talk about, to repeat. I just put them on a list. We can discuss the order of things later as you wish. Probably a lot of things are quite familiar from the recent past, whatever courses you attended. We can have a look at these questions, and then any time we can come back to points that like if you have remarks or questions. Computational cost and memory cost. Let's think about histograms or something. Sorry, yeah, you want to say something? Yeah.
My question is that what does it actually mean by supervised learning?
Mm-hmm.
Either it's like any training data with labeling is like the labeled data we use for training is the supervised learning, or it's something else?
Yeah. So what is supervised learning? Supervision always means you have a target label. There's also the notion of self-supervision, which is like where the target label is the data itself. For example, you can, okay, so supervised learning means there's a target label y. So an input location, input vector, and a target label y. And whatever you want to do, for example, you want to predict y, this is the prediction goal, and you use this to find the parameters and potentially also hyperparameters of your classifier. What is self-supervision? I think that's an important notion also. So this is supervised. What is self-supervised learning? Can you give an example? Sorry? We don't have that y, but we have something else. So in self-supervised learning, there's something like, okay, we have an x again. So that's the simple part. And the prediction target is some function, let's say, of some other x or the same x or whatever. No? So you have a bunch of data and you say, okay, I want to train on xi, and the training target is somehow also derived from my x's. Yeah? Like if you think about the training of large language models, no? The pre-training step is a prediction task on the text itself. No? So it says, I was lucky, and then asks, guess which word fits in here. No? But as a basis for this guessing task, it takes an existing sentence. So it already kind of knows. So the xi is this loopy sentence here. And the xj in that case would be the same sentence, just without the impairment. No? And then you could guess something like 1 day or so would be a plausible fill in or so. No? And from that, you can set up a training objective that is like supervised training, but not with like an extra label or so. Yeah? So this is what you would call self-supervised.
We use some like training data for use a portion of the training data as the XJ.
Yeah. Yeah, part of the training data is the XJ. Let me give you a different example. So not text, not the pre-training of large language models, but instead something like learning motion. Yeah, you can take a video, can say, here's a video frame. There are past frames, for example, if you want to look at this, and so on and so on. And then you take the future frame as a prediction target there. No? And then you can, that way you can learn like motion trajectories or things like this that are consistent with the data without having the need of someone providing labels. No? So this is the common self-supervised training trickery. No? Yeah. There are also, it doesn't need to be sequential data. I think it's particularly easy to illustrate on sequential data, but you can also come up with other scenarios. No? For example, in forensics, this is my research topic, when it's about detecting modifications in images. One technique is to say, okay, if this is my image, and the image is a digital image that comes out of a camera, then it also has EXIF metadata, and there is, for example, the gamma factor, or so is, and so on and so on. And then you can learn a predictor that, given a patch of the image, maps to a certain gamma factor or ISO setting or whatever, like different camera properties, and then uses this to train a predictor for whether the image is consistent with the metadata or not. So in that sense, it doesn't need to be sequential data. It can be, like you can set up anything that sort of explains things from itself or from the structure of the data itself. Yeah, that would be the self-supervision principle. Okay. Sorry, let's go back to the questions. Yeah, and unsupervised means we're not even aiming for any label for supervision, but we're only looking at the distribution of the data. Yeah? Like, for example, clustering is a typical unsupervised task. If you say, okay, I have a couple of data points here and a couple of data points there, then from their structure in the space, we're sort of inferring, okay, these are probably two different groups of data. Yeah? We will come to this in the course of the lecture. So that would be unsupervised then. Okay. So let's talk about histograms really quickly. So let's say we have n samples, d-dimensional sample space. Sorry, what sentence is this? It's a bit broken. In a d-dimensional hypercube with side length 1, somehow normalized. Yeah. Now we want to discretize this space in a histogram with b bins per dimension. So this would be one dimension with b bins. Now we have d of these dimensions. So it goes on like this. These are also b dimensions, then third dimension, fourth dimension, fifth, and so on and so on. All of them subdivided into b bins. So if we want to represent each of these little histogram bins with a number, I don't know, let's say an integer number or something like this, what would be the memory requirements for holding such a histogram, uncompressed and so on, of course, in space? And then we can continue. Like, what would be the space requirement for this? We have d dimensions, B bins per dimension. How many memory cells do we need? B to the power of D, yes, in that order, no? Your B raised to the power of the dimension, no? So this means the dimensions are in the exponent, the B are the bases here. So this means if we increase the binning, we increase the basis. If we increase the dimension, we increase the exponent. Which one is worse, increasing the basis or increasing the exponent? What? Exponent is worse, no? Yeah. So this means if we're using a histogram as a representation, we have to keep in mind that when the dimensionality grows, this quickly creates problems, no? Whereas maybe a finer binning, maybe this is something that can be afforded, no? Depends. So let's say we have a kernel density estimator, a box kernel, the way how we discussed this, no? How could we implement this in a naive way? So let's say the kernel window are k bins raised to the power of d, because it's a d-dimensional kernel also. What would be the cost for a naive implementation of this? So now we have a so the kernel. In our slides, we just said the window size is 1/2, no? And we scale it up front with this divided by h. You can also pull, like if you actually implement this on a computer, you can pull the h in your kernel function and say, okay, I have k bins here. I have my d dimensions. Yep. And then, like for every location in the space that I want to evaluate my density on, I have to check this neighborhood. Yeah? So this neighborhood, if we look at this is essentially the same as a small cube in that histogram, no? So per location, this incurs cost. So the kernel incurs cost per location of kernel raised to the kernel size, like number of bins raised to the power of d. So if we really wanted to explicitly have a density estimate throughout the whole space, then the total cost would be, like for all locations, what would be the total cost? This is easy, huh? Isn't it? Like we check here, we check here, we check here, we check here, we check here. We discard boundary effects because we are lazy. We check here, we check here, we check here. And then total cost is? Sorry? Yes, we just have to multiply things together. Yeah, that's all. K raised to the power of d times b raised to the power of d. No? Okay. Of course, no one would implement it in such a way, no? Because it's a total disaster. But then it needs more trickery, and I'm not sure whether we want to discuss this now, to implement it in a more efficient manner. No? I think generally, if the number of dimensions grows, then this is probably not an attractive representation for the space. No? Yeah. Yeah, sorry, this is a kind of transfer question. Why is the lecture sampling algorithm bad in high-dimensional spaces? Sampling algorithm. How did it work? What was the idea of that? So was this with this cumulative density function thingy, right? Let's draw a quick picture. You will study this more on next Thursday, by the way. Let me announce this with Sheetal. But just for the sake of having something to talk about, if this is the PDF, no? The idea of the sampling algorithm was to calculate the cumulative density function, CDF. What would it look like for a thing like this? Well, okay, it increases where we have some probability mass here, no? And then there's not much action if we have no probability mass. And here we have a little bit of probability mass, so it increases less. So here probably we need a 1, because it's a function that ranges between 0 and 1. Yeah? Okay. And then we can draw a number here, check where we intersect the CDF. And this is the random number here that we draw. Yeah? Okay. But in the context of this task, like what is the problem here of the sampling algorithm? Is it difficult or is it boring? I find it hard to read your silence. If it's difficult, we have to break it down somehow. If it's boring, okay, well, we can just get done with it. How could we break this down? Well, there must be some link then between the upper blackboard and the lower blackboard. Otherwise, it wouldn't make any sense to have it in one question, right? Because we were just discussing higher dimensional spaces or increasing the D. For a histogram, it's not so beautiful. How does it connect to the sampling algorithm? Okay, where are the numeric students? Computational engineers? No? Okay, computer scientists? Other folks? Yeah. Can you, the beginning, I didn't get it.
Yeah, so the number of bits does increase exponentially with higher dimensions.
Uh-huh.
Yeah, so and we need to calculate the CDF for each bit.
Uh-huh.
So it's complexity-wise.
So yeah, so the number of bins increases exponentially if we ramp up, like if we increase the number of dimensions. We're going black. If we increase the number of dimensions, we have this little exponential problem up there. Now let's try to link this to the CDF calculation. How, okay, let's start with the probability density function. How could we implement like a couple of lines of Python? How can we represent a probability density function? Just like what options are on the table? Certainly there are different possibilities, but it's not clear. Well, you need some functional form, yeah, something like anything. No? You can say, okay, I don't know, I approximate this with Gaussians, looks pretty, no? Like a weighted Gaussian or so would be one possibility. No? But in fact, if we think about statistical learning as like in a frequentist sense, no? Then maybe a more direct way is to actually say, okay, here's my data. The data is what forms the PDF. So I count the properties of my data that I'm interested in and represent this in a histogram. No? So this is the most direct, let's say, way of representing it, like with like any other representation as a mixture of Gaussians or splines or so. Yes, it's also possible, but it's more complicated, no? And it's already some abstraction on top, no? But the first approach would be to use a histogram, no? And then count occurrences and somehow approximate the structure of the data, very much as we had it in this picture here from Bishop's book. No? So Bishop was starting analytically by saying, okay, here's the green curve, and now I'm drawing a couple of samples from that green curve, and here's my histogram. But in practice, you download a data set, you start with the data points and say, okay, this is my whatever, this is my density, no? And then from there, I want to draw new samples. So I use this as a basis for my sampling algorithm. No? So in a way, a histogram is one way to get a categorical representation of your data, which is what we need for the sampling algorithm. Yeah? So if we have a histogram here, everything is fine. In principle, we can calculate the CDF super efficiently by just calculating a running sum over these bins. But of course, only if D is small. No? Otherwise, it totally just escalates in terms of like how many entries we have to sum up. Yeah? That's the whole point. Other than that, it's fine. It's perfectly fine. Okay. Yeah, so the lecture sampling algorithm is bad in high-dimensional spaces because you need to calculate this cumulative density function, and most likely, in order to calculate that conveniently, your underlying representation is a histogram, and then it's subject to the same scaling properties as discussed before. Yeah, it would be like the answer. here's a quick question. Tuning the density estimator hyperparameter on the training data. Okay, we said we shouldn't do this, but let's just say we somehow ignore this advice, or we screw it up, or whatever. And the question is, what happens then? No? So what exactly happens when tuning the hyperparameters for the Parson window density estimator and the k-nearest neighbor density estimator on the training data instead of some held-out validation data? Yeah? So we directly use the training data that we have to also determine the hyperparameters. Let's trace this like step by step, like what happens. Yeah. Why? Yes, but let's go more into detail. So, sorry, let me repeat what you said. So you correctly said it's going to overfit. The hyperparameters the choice of hyperparameters will not be a good choice if we fit it on the training data. But let's specifically look into the Parson window estimator, for example. Yeah? What is the hyperparameter of the Parson window estimator? Kernel size or window size, yeah. Mm-hmm. Okay. What do we have? What objective function did we look at in what objective function did we look at in order to find the best window size? Sorry, usually I'm speaking about window sizes here. It's the same thing, but nevertheless, yeah. What was the objective function? It was a log likelihood for the samples, like to assess. Yeah. So the objective function was essentially going over these samples that we are using to assess the quality of the window size. Yeah. Some running index, I don't know, I. And say, okay, we take the logs, this has numeric reasons, of the interpolated density or the estimated density, yeah, with a certain window size. So we can write this here with given age, like to make it explicit that we evaluate this for one specific age, window size age. For our test samples xi. So what does that mean? What if these samples are the same samples that are used to create the density? Let's draw a picture, if you know, yeah. Two-dimensional space, maybe, no? We have a couple of training data points. So this is our data. Now we're looking for a good window size to represent this density. Yeah? For example, we could try this window size in both dimensions, no? Two-dimensional. You could say, oh, okay, so here around this sample, it assigns a bit of probability mass in a volume with this side length. Yeah? Also around that sample, it assigns a bit of probability mass at like in a box around that. Here it piles up. So we have a higher probability here, like a higher density here, no, than here, because these two overlap and they add together. But that's fine. No? And then it continues like for all samples. So here again would be a little overlap, so a little bit more density, and so on and so on. No? Okay. Now we check the log likelihood. So we take the same samples again, or a subset of those, yeah? A subset of these very same samples. So 1, 2, 3, these are our favorite evaluation samples, yeah? And we take the probability mass that we have here at these locations, and take this as a quality measure for this window size. No? And what will be the probability mass of these samples? Sorry? 1 divided by, sorry? Yes, and divided by? So this is correct, but there is another factor. Where were we? This is our final equation, no? So if we have the number of samples in our window, okay, like 1, for example, divided by the total number of samples, divided by the volume of the window. Ah, this is bad. So this means for these 3 samples, we will get something like 3 divided by n, okay, n is fixed, divided by h squared. And then we will find out if we try a different age, if we try an age that is half this size, that we have a benefit of that. Because all windows will be half in size, holes are created from that because the windows are smaller. No? Maybe our density disconnects. In some situations, this could be disturbing. In our situation, it's not, because we are checking the center of that windows anyways, because we're using the exact same data. So we evaluate our target function. Turns out the second objective function is much better, because we divide through a smaller number. Okay, this is better. So I don't know, if someone trained us to follow gradients, we say, oh, this is a promising gradient. Let's make the window smaller and smaller and smaller and smaller, and we keep winning. No? So at the end of the day, if we make the window as small as we can with our numerical limit, we will find out this is the best window size. No? Because it's a super small number by which we divide, so we have maximum reward. And this is why it's so pointless to tune the hyperparameters on the training data. Yeah? Like it's not informative. Does that make sense? What would be the alternative? I mean, you can say, okay, I see this is leading nowhere. What would be the alternative? If I had data, like some independent data points there, then I would have to make a trade-off. The trade-off that I would be expecting here is to say, okay, maybe indeed these data points are representative, yeah? But of course, I have a new draw from the same underlying distribution to have my validation data. Yeah? So this means maybe I have an observation here, maybe I have another observation here, maybe another observation here, maybe another observation here. So we could say this is not so different from the other data that we have drawn. In fact, it's very similar. But the more or less the distance you could imagine of these validation samples to the observed samples kind of constrains our window size a bit. No? So if we make the window size too small, then we are sorry that we assign a 0 probability mass at that location. So it's not bringing us a benefit in our reward function anymore. Yeah? So in that case, it might be better to still keep the window a bit up, no? to include, like to cover a larger area of the space in order to also cover these unseen validation samples. Yeah? So that's the spirit of the unseen validation data. And then still, I mean, having h raised to the power of d in the numerator is still a powerful incentive to make the window small, but at least we have a bit of a counterbalance here. Okay. So third question is maybe a no-brainer, I don't know, but it's always hard for me to predict what is easy, what is harder. So if we think about the very last slide in our slide deck, there was like, yeah, if we have a kernel density estimator or if we have k nearest neighbors, we could actually interpret this or use this as a regressor, or we could use this as a classifier. So it's not necessarily that we are limited to using this as a density estimator, and vice versa, more or less. Yeah? So let's maybe illuminate this aspect a bit more. And there are probably easier and harder aspects of this. What analogy would be easy to see from your perspective? Nothing. Let's start with the k nearest neighbors. You probably already know this as a classifier anyways, right? Do you? Yeah. How does k nearest neighbor work as a classifier? Oops. How does it work? Yeah.
Randomly set the number of classes center of each class, and map both other data to each center, each class, based on the distance between the data.
Yeah, like we have a certain query location. So we want to know what is the class here. No? Yeah. And then we look for the k closest other data points and say, okay, let's see what classes they have, what class labels. No? And then we can make a majority vote and assign that to this class. No? Right. In a very similar way, you can also build a regressor. Yeah? So you can say, okay, regression. So we have a continuous prediction goal. No? So it's somehow covered by our data. No? Now we want to know what is the value here at this location. No? we look at the 3 nearest locations, for example, form an average. Okay, we don't hit it exactly, but okay, this is the way how life goes. No? But this is the approximation for the value at this location. No? Okay, so this is the regression. And if we think about it, the density estimation is actually similar to a regression task in the sense that having a sample can be considered as a 1, but then having no sample can be considered as a 0 kind of fish. Yeah? So we have a distance penalty, could say. No? It's not exactly the same thing, but still, no? We can say, okay, if we are interested now in the density value at this location, we look at the 3 nearest samples and then calculate, for example, the maximum distance of these 3 would be a valid way, or something like an average distance of these 3. In any case, it's like an inverse, you could say, regression task. No? That the further away you are from these observations, the further towards 0 the value is pulled. No? But other than that, it's very similar in spirit. No? And for the Parson window estimator, I think for the Parson window estimator, the classifier is maybe not so obvious. No? But if you have a situation where you have labeled data, what you can do, now I'm running out of space. Maybe I continue up there. Sorry for the mess, but so for the Parson Windows classifier, you would say, okay, if I have labeled data, I separate my data by label. So for example, I have these little rectangles, and I have circles. Then I interpolate one density for the rectangles and one density for the circles. And then if I get a query for a certain location, then I make a maximum likelihood response comparing the square density with the circle density. Yeah? Makes sense, right? And for regression, this is would be a standard kernel-based regression. It's very, very similar to the k-nearest neighbor in the sense that you take neighboring samples and you take the kernel function as a weighting function to take these neighbors into account to get a prediction for the point of interest. Yeah? Okay. Yeah. What will we do next time? So first of all, I'll put the new material, I'll put it a bit earlier online than yesterday. Sorry for that, but I had this urge rework the slides. So in case you attended pattern analysis last year and are now in this class, there are a bit of changes in this slide deck. But it took me a while to do it. I'm sorry for the delay. I promise it will be faster this week, so it will be Thursday or Friday that we have the new material online to give you a bit of a pre-warning horizon. I also heard that there's a mono stereo sort of issue in the videos. I'm going to look into this. Hopefully I can fix this. On Thursday, there will be a meeting held by Sheetal. It's not recorded, but I think it will be very nice because she will look more into this like kernel-based interpolation. I think they're preparing a small demo or so. So I think it will be helpful to get a more intuitive understanding of things that are going on. Yeah? So these are our short-term goals, and then we just go step by step, week by week, and continue like that. Okay? All right. Then let's conclude the meeting for today. Thank you very much, and see you then.